Hello, everyone, and I hope everyone's having a good day. Today, we are actually going to be finishing up our atomic model lessons. So, remember that Bohr's model? Bohr's model actually worked really well and was able to predict new things for hydrogen. Unfortunately, it wasn't able to predict anything past hydrogen, any element that was bigger than hydrogen. So, as I was saying, Bohr's model really only worked for hydrogen. And one of the biggest problems with Bohr's model is that if it was actually true, the electron would actually fall into the nucleus. Because when you have something revolving around, that orbit actually, it declines a little. It decays a little. And fun fact, the moon is actually decaying too. The moon's orbit is decaying a little bit every so often. The thing is that it's not decaying at fast enough rate that we are actually fearful. So don't worry about that. So the Bohr model doesn't work perfectly. So we have to do some updates. And there were a couple more dead white guys that were able to help us out. Let's see. I forgot what year he was. I think it was, hold on, I can figure that out. Let's take a look-see at what he was. I know his name was de Broglie. And de Broglie, basically, he studied waves, light waves. Yeah. And let's see. Can't find the year. Oh no, where is the year? That makes sense. Um, and so waves, as we know, and we're going to say about 1925. In about 1925, 1925 date, 1926. Light waves, as we know, work very different than like particles. Light works weird. You can bounce it off mirrors in a weird way. It goes around corners. If you shine a flashlight and I'm around the corner, I can see it, as opposed to if you shoot some water, it won't hit me if I'm around a corner. I can hide around a corner, right? So light waves work really different. And de Broglie was responsible for finding the wave like nature of electrons. And basically, what that means is that electrons can act like both waves and particles. And they do. And that's one of the reasons why Bohr's model wasn't working. It's because we were treating the electrons as if they were a hard sphere, as if they were a sphere. And they don't act like a sphere. They don't travel like a sphere. They travel like, well, like a light wave with more mass. There was another scientist by the name, and you might have recognized him, of Schrodinger. And he was about 1926. And he figured out how to map out basically what a light wave is going to look like in any given area. He was a mathematician, and he found out statistically how to match out a wave. And final scientist that we want to talk about is Heisenberg. Heisenberg, about 1927. And his major conclusion is that you can't know everything about electrons. You can only know a little bit about electrons. And what does that mean? That means that we can know where they should be, can know basically the boundaries of electrons, but not the specifics. For example, let's say one of your parents calls up school, just wants to know where their child is, right? When they know that their child is in school, they know that their child has to be within the building, right? But they don't know specifically what room or what chair their child is in. That's what it is. That for our electron, we can know that it has to be within this boundary, within this building, but we can't. Not that we won't. It is impossible for us to know. And that all has to do with the fact that electrons act like waves. We can't know everything about it. And so we came around with this new model of the atom. And this new model actually has 3 names to it. First name is the quantum mechanical model. The second name is the wave mechanical model. And the third name you have to know is the electron cloud model. They're all the same thing for this. They all are the same name for this one model. Model. Okay. And big things we have to know that electrons don't actually exist on orbits, like Bohr said. Electrons actually exist in orbitals. And what an orbital is, an orbital, it's the highest probable location of an atom. Just like if we look at a child, if we talk about a student, they have a high probability of being in school during the day. We don't know exactly where they are, but there's a probability that they're inside of the school. The electron has the highest probability of being inside this orbital, and the orbitals are in shells. And if you think of literally the shell of a ball or the shell of an egg, that's literally where the electrons are, around the nucleus. So if we have our nucleus, and around it, instead of calling them orbits, we now are going to call them shells. Because this is actually, and you can't see it, but they're actually 3-dimensional spheres. This is a 2-dimensional picture, but you have to imagine that in all 3 dimensions, that's what this looks like. And so these shells are where the electrons are. There are orbitals in the shells, and the electrons, that's really what the shells are. The shells are made up of orbitals, and the orbitals are the highest probable location of electrons. And that is really the most advanced model we have for the atom. The most up-to-date model. Isn't that super cool? Thanks for listening, everyone. I'll talk to you soon. Bye. Oop, that was the wrong button. Hold on. I got it. I can do this. Bye.